In this lesson, we're going to talk about Objective 8.1, Introduction to Acids and Bases. So this learning objective states that we should be able to calculate the values of pH and POH based on Kw and all the concentration of all species present in a neutral solution of water. So let's just do a quick review of Bronsted-Lowry. We had learned of this in Unit 4, Chemical Reactions. So Bronsted-Lowry states that an acid, so HA, this is the notation, where A will be some type of anion. This acid will be a proton donor, and our base, which would have this notation BOH, B will be some type of cation, is a proton acceptor. So when we look at this reaction below, this is actually a neutralization reaction, where in this neutralization reaction, we have HNO3, which is our acid, and NaOH, which is our base. So I knew that HNO3 was my acid because the H is leading first, and then the NO3 is some type of anion, which is the nitrate ion. And then we have NaOH, where I can see the Na is some type of cation, sodium, attached with a hydroxide, OH. So one thing that, just to review kind of what we learned in Unit 4, is that since acids are going to be donating hydrogens and that base will accept it, we also need to talk about conjugate acids and conjugate bases. So remember, acids, once they release that hydrogen, you're going to make a conjugate base in the products. And then our bases, once they accept that hydrogen, that becomes the conjugate acid. So looking at these two products, the water and the sodium nitrate here, and I want you to think of it as, I know it's not NaOH all gaining a hydrogen. Think of sodium as going to be a spectator, so it's not really there. Also, the nitrate's not really going to be there. So here, that OH would gain a hydrogen. All right, so here, this would be my conjugate acid, the result of your base gaining a hydrogen, and then this NaNO3 would be our conjugate base. All right, so let's talk about the concentrations of the hydrogen coming from the acid and the hydroxide coming from the base, okay? So concentrations of hydroxides, OH minus in brackets, because remember brackets mean molarity, concentration, and hydrogens, H positive, are often reported as something called pH and POH respectively, okay? So I want to zoom in right here. So the P in pH and POH actually stands for power or potential. I generally think of it as power rather than potential. And so here that P stands for a power of hydrogens for pH. And then for POH, it is a power of hydroxides. Now, I want to mention something before I teach you these equations, something about hydrogen, which we did talk about in Unit 4. So remember we talked about the hydrogen ion is highly attractive. It is very unstable to exist on its own, because you had to envision an H positive, what that would look like on the molecular level is it would just have one proton, okay? And so here, when you have just a single hydrogen positive in a solution, let's say, it actually just really cannot exist on its own because it's such an attractive molecule, okay? Or I guess we should say atom. But here, it's actually going to attract itself to a water molecule, okay? But yeah, it is very weird that hydrogen can't exist, but basically it's going to attract itself to a water, which this is going to make H3O positive, hydronium. So essentially what's going to be happening is we are going to be using more hydronium rather than hydrogen. But please note that hydronium is the same as hydrogen. Just this is the more actual way of trying to represent a hydrogen ion. They like to say H3O positive is considered the hydrated form of the hydrogen ion in aqueous solutions. So here H3O positive is the hydrated form of hydrogen ions in an aqueous solution. So I know it's not ideal looking at this because it's kind of weird to see H3O positive, but we just have to get familiar with that, okay? And what's actually kind of interesting, why isn't the pH scale pH3O? I don't know, but I think it honestly comes back to a long time ago. They just got so comfortable talking about pH. Okay, so let's talk about pH and POH. So I told you that pH measures hydrogen concentration, while POH measures hydroxide concentration. And so these two equations will be on your equation sheet. So if you actually get your equation sheet out now, go to the back page, look for the acid and base section, you're going to see these equations. So here pH is the negative log of the hydronium, or you can say hydrogen, same thing, concentration. Okay. Now I cannot remember, I should probably look. Now let's say you want to, instead of solving for pH and you want hydronium, here hydronium concentration equals 10 to the power of negative pH. All right. So let's dive in more about what this pH and POH scale is. This scale is technically a logarithmic scale. Okay, so what that means is that if there's an increase or decrease of an integer value, it's going to change the concentration by a 10-fold. I like to think of this as a shortened way of using scientific notation. But again, I know some of us haven't been working with logarithmics yet, but here's the thing, you're going to have for sure these two equations. Okay, which I haven't told you the other one. So here, POH is the negative log of hydroxides. Okay, but yeah, you're going to definitely have these two equations. And again, it's just more of a shortened way of using scientific notation. Okay, but I just want to write this right over here for us to reference later when I get back. pH and POH scale is a logarithmic scale. And so here, if there was an increase or decrease of an integer, value changes the concentration by 10-fold. All right. And then lastly, for the POH, to go the opposite way, hydroxide will be 10 to the power of POH. Again, if you actually haven't done, I just want to show you right here, you don't have to write this down. The reason that we can change the equation that way is because if you take E on your calculator by both sides, here that ends up getting rid of the log function. And so that negative will end up coming over here. So that's why it's 10. E stands for 10 times. That's why it will be able to get rid of that log, is by doing E to the power on both sides. Just kind of a fun fact of how that math works, okay? In my previous video, when we were talking about writing out acid-base reactions, I had mentioned that water actually spontaneously donates a hydrogen to another water molecule, which creates that hydronium and hydroxide. So it is kind of weird, but water technically will have some ions present, but it's so minimal that it probably will not even pick up if it was on a conductivity probe. So we tend to just say tap water, we tend to just say DI water will have no ions at all because it's just water. But technically there will actually be a minimal amount, but nothing that would be read on a probe or anything, okay? So since water does auto-ionize at a very small rate, we do have to mention an equilibrium constant associated with water. So we denote this by Kw. So in this unit, we're going to have a lot of different Ks. I know we've already talked about Kc, AQ, Kp, Kp being pressure. In this unit, we're going to talk about all the different Ks, especially when we are in our acid and base unit. So they denote Kw specifically for water. So on your equation sheet, you're going to see Kw equals the hydronium concentration multiplied by the hydroxide concentration. And you will see that that Kw is 1 times 10 to the negative 14. But this is only going to be true at 25 degrees Celsius, okay? What this means is, in pure water, pH will equal pOH is called a neutral solution, all right? So at 25 degrees Celsius, there's this thing called pKw, which would just be taking the negative log of the Kw, which pKw will be 14. So taking the negative log of 1 times 10 to the negative 14, we get our pKw equals 14. So looking at this equation up here, which is on your equation sheet, if we take the negative log of the Kw, and let's say we took the negative log of the hydronium and negative log of the hydroxide, we now get another equation that's on your equation sheet, 14 equals pH plus pOH. Okay, I think this equation ends up being a little bit more favored than this one above, just because the one above with Kw is going to have scientific notation, and we already know that's the most difficult to put into a calculator. All right, so since we have talked about Unit 7, we know that K is affected by temperature. So the value of Kw is temperature dependent. So the pH of pure neutral water will deviate from 7 at different temperatures from 25 degrees Celsius, all right? So you are going to need to know this because there have been problems where they ask you about a Kw that isn't at 25 degrees Celsius, so you have to think of it on a conceptual level. So here, if there's going to be an increase of temperature, you're going to end up increasing your Kw. You scroll up to the top looking at this equation. So if we increase the temperature, we're going to increase Kw. So if we know hydronium is X and hydroxide is X, and that makes X squared, with that Kw increasing, our X will increase. So here you'll have an increase of hydroniums and an increase of the hydroxides. Here, you can think of it as our pH will decrease and our pOH will decrease, okay? All right, so just to kind of show you some, just from the internet, looking at different temperatures, here I'm going to show you what Kw is at 40 degrees and 0 degrees. So at 40 degrees, Kw is 2.92 times 10 to the negative 14. So you can see in that increase of temperature, 25 to 40, your K did increase. Now, even though it wasn't even that much, you can see that it definitely increased. And then with 0 degrees Celsius, our Kw gets smaller at 1.14 times 10 to the negative 15, not 5, my bad. Here, if you took the square root of both of those values, it's going to deviate from our original, which we technically haven't talked about, but you could probably put it together. Here, we know a neutral solution is 7. So if our Kw is 1 times 10 to the negative 14, and we took the square root of that, that's 1 times 10 to the negative 7. pH is 7, pOH is 7. That's why it's out of 14, okay? All right, few things, just a common misconception. A lot of students, or adults, I guess, too. Acids and bases, pH and pOH scale is only in a range from 1 to 14. This is false, okay? Here, it can be less than 1, and it can be greater than 14. Again, that's supposed to be a 1. I don't know why it looks like that. Okay, here, if your concentration is high enough, you're just going to have a lot of concentration, and it is what it is, okay? I mean, you can't help if you're working with a stock solution of HCl and it's, 12 molar. If you took the negative log of 12, it's definitely going to be in the negatives, okay? That's completely fine. I mean, you're not going to be working with a 12 molar solution all the time. You're going to be working with things that are less than that, especially in this unit. Another thing is it can be greater than, all right? It just, most of the problems have just been based off our water being at 25 degrees Celsius. That's why this scale goes from 1 to 14. 14 being that 1 times 10 to the negative 14, but you took the log of it, so that's why it's out of 14, okay? All right, last little thing that we're going to do. Let's talk about how all of this relates together when we talk about acids, neutral solutions, and bases at 25 degrees Celsius. So if our acids are going to be less than 7, okay, on a pH scale. I should probably write that. And so our bases on a pH scale will be greater than 7, while neutral, like we had mentioned earlier, equals 7. So a pOH scale you probably will not touch on, but it doesn't hurt to talk about it. But the pOH scale is going to be the complete opposite of a pH scale, because a pH measures hydrogens while our pOH measures hydroxides. So if acids have a pH less than 7, they're going to have a pOH that's greater than 7. Neutral will still be 7, and then pOH will be less than 7 for bases. So let's talk about the hydronium and hydroxide concentration. So a pH that is less than 7, we're going to have a hydronium concentration that is greater than 1 times 10 to the negative 7 molarity, all right? And then if it's going to be a hydroxide, we'll have something less than 1 times 10 to the negative 7 molarity. For a pH of 7 for neutral, you're going to have equal amounts of the hydronium and hydroxide. So they're both going to be 1 times 10 to the negative 7, 1 times 10 to the negative 7. And then I'm sure you can fill out that last row here. Bases are going to have hydronium that is less than 1 times 10 to the negative 7, while our hydroxides will be greater than 1 times 10 to the negative 7. Now, one thing to kind of just leave you with to end this video is just remembering that acids and bases are dissolved in water, okay? They are solutions. They are aqueous solutions. Okay, I might just write that. So here, the fact that they're dissolved in water, and we already know that water is going to be auto-ionizing at a very small rate. That's why just because our acids release hydrogens, there will be some amount of hydroxides, but very, very minimal, okay? But you just have to remember, all of this is connected with water. There's a reason why all of this goes together, and this goes back to neutralization reactions, okay? All right, the next video should be 8.2, pH and pOH of strong acids and bases.